Yeah, hello everyone. Welcome back to the afternoon session of FRINGE 21. You're here in the third earthquake and tectonic session, and we have five very interesting presentations. I'm sharing this session. I'm Henriette Sudhaus together with Paul Landgren, and yeah, you can post questions on the Slido on the site, and we will do a question and answer session after the five talks. So you can post your questions anytime. And without further ado, I would like to introduce our first speaker. This is Simon Daou, who has been working in University of Oxford. And he gives us a presentation of post-earthquake fault growth imaged in the Qaidam Basin. Please, Simon.
Yes, thank you. I'm trying to share. I don't see it anymore now. Here we go.
This looks good.
Yeah?
Very good.
All good? Perfect. Okay, thank you. So, hello, my name is Simon Daou, and I'm planning today to discuss about the observation of very long-lasting post-earthquake signals that have been imaged within SAR in the Qaidam Basin. So, where are we? Can you see my mouse here? Yeah. Okay. The Qaidam Basin is one of the largest active intramontane basin inside the Tibetan Plateau that is bound by the Altintag, the North Shaddam Trust in the north, and the Kulun Fault, or the Kulun Shan in the south. There, about 4 to 6 millimeters of convergence are accommodated across shortened sediments and basement faults. And the region has experienced active seismicity these last decades, and more particularly in this area, that is here, where we experienced 3 magnitude 6 earthquake. The first one in 2003, which is in red, followed by a sequence of magnitude 5 earthquake in 2004. And then a magnitude 6 earthquake in 2008, and in 2009, followed by 2 aftershocks. So the objectives of this work were multiple. Trying first to disentangle, but to get insight into the fault geometry at depth, and more particularly for the 2008 deep earthquake, which has an ambiguity of fault geometry with a solution dipping to the north along a shallow angle plane, or a solution dipping to the south along a high angle plane. And then try to link this crystal shortening with what's happening at depth, which has a consequence about the evolution of the Tibetan Plateau and the dynamics. And also, the second objective, let's say, was trying to capture both the slow inter-earthquake and post-earthquake surface displacement jointly with the co-seismic ruptures, with the time series analysis approach. So we processed both NVSAT archive, which are here in blue rectangle, and the Sentinel-1 ascending and descending track for this area, and identify several processing challenges. The first one is linked to the, as we saw a lot during this FRINGE meeting, to the bias associated with multi-looking and the integration of small baseline interferograms, and more particularly within the Qaidam Basin, because it's a very arid environment. There is a lot of crops, there is crops and farm, and there is also the presence of salts. And when there is a raining event, which are sparse, it creates quite strong phase change between 2 successive acquisitions, which leads to decorrelation or unwrapping error. And so therefore, if we have a seasonal model like this one in time with abrupt change during raining event, and if we only include a small baseline interferogram in our network, there is a chance to create a bias in our time series analysis, While if we also include those long baseline interferogram between drying events, then we can mitigate those effects. The second processing challenge is linked to the fact that we are in a periglacial environment. And so the mean average temperature at high elevation is below 0 degrees. So there is permanent ice in the ground, which is the permafrost that can be modeled, as for example, in this probably map distribution for Gruber et al. Evidences of frost-heave processes are also everywhere in the landscape, as attested by those frozen lakes, those thermokarsts, or those polygon cracks. But also in high relief, we see a lot of gravitational mass processes like solifluctions that are linked also to these frost-heave processes. So our approach to deal with those challenging was to process both short and long wavelength interferogram in order to aid for the unwrapping. And we process with the NS-bus processing chains that include few correction on the wrap phase, like for example, orbital or atmospheric correction that we apply on the wrap phase. In addition of that, we also compute a stack of coseismic interferograms that we also remove from all the interferograms that were containing the coseismic fringes. And so after that, we were able to multi-look, filter, in order to be able to unwrap at large scale. And after this unwrapping step, we reintroduce all the correction, what we previously applied, because we don't want to remove anything, and perform the time series analysis. And then to deal with these surface processes, what we did is that on the cumulative displacement map, we remove a long wavelength ramp on the stable bedrock, and then decompose our signal into linear and seasonal term in order to detect pixels that are affected by very high seasonal deformations linked to those freeze-off processes, which are here in this map in red, and that have been intensively analyzed in this publication that you invite you to look at. But for this tectonic analysis, what I just did is to use this map of high amplitude to mask areas that we will not analyze in our tectonic interpretations. And so let's first look at the envisaged result. You have here a snapshot of cumulative displacement in time, which are dominated by the coseismic ruptures. We have this long wavelength associated to the deep 2008 earthquake. And after this shorter wavelength signal associated to the shallow source dipping 2009 earthquake, which is segmented and show both uplift in red and subsidence in blue. We don't have the 2003 earthquake because the data start after it, but we see in the 2003 earthquake area a slow increase of surface displacement not associated with any seismicity that we analyze later as post-seismic signal. But let's first look at this 2008-2009 sequence that we model with the ground software, which is included in Pyroco. And for the 2009 event, we invert for 3 source dipping high-angle thrusts that are with the base fit solution in blue in this map, or with all these blue lines in profiles. While for the 2008 event, what we did is we perform 2 distinct inversions, one with a source dipping plane and one with a north dipping plane, and invert both coseismic and post-seismic. And we observe a very nice collinearity between the coseismic, which is in coral color here, and the post-seismic, which is in orange, for the north dipping low angle solutions. So we conclude that probably here we have a pop-up structure which root under this to this low angle decollement at depth. Let's now move to look at the post-seismic signals that follow these 2 sequence of events. We have on the left panel the 2009 coseismic, the 2009-2011 velocity, extract from MVSAT, and on the right, the 2014-2019 post-seismic as seen from a descending view also with Sentinel. And what is remarkable here is that while the coseismic surface displacement pattern doesn't match this young Yolombo-Langshan range on the coseismic, slowly in time, the post-seismic surface displacements have lobes towards the satellites that match almost perfectly the the young geological structures. So to look more in detail, what we did is that as we have both ascending and descending, and as the GNSS doesn't indicate any strike slip motion in this area, we decompose into a shortening component perpendicular to the range and a vertical velocity in this figure. What you observe is that the Longbulang range is moving to the north, which is in red in the shortening velocity, but also some part of this range, more particularly the southwestern part, is also moving to the south. There is no far-field shortening, and there is several maxima of verticals that are associated with identified anticline in the geomorphology that I enumerate 1, 2, and 3. So from this signal and from our geomorphological interpretations, we deduce this schematic structural interpretation and infer that the observed this long-term post-seismic deformation is not due to slip on a fault in an elastic medium, but due as distributed fault growth induced by those two earthquakes. As I said, we also observe a strong post-seismic deformation in the 2003 earthquake area. Again, I don't have the post-seismic of the earthquake, but what I have is velocity from 2003 to 2006, from 2006 to 2011, and from 2014 to 2019. And what we saw is that from 2003 to 2006, at the beginning, the signal is decomposed into a broader signal within the Longbulang-Shan, and a sharp and asymmetric signal at the topographic front, which is this Delinga anticline. And slowly in time, this signal decreases, but still is higher than the far-field shortening, interseismic far-field shortening, and is only concentrated within this Delinga anticline in time. So here again, we perform two decomposition into shortening and vertical. And we observe that the shortening is mainly concentrated at the sharp contact between the anticline forelimb and the quaternary deposit in the basin, while the vertical is concentrated on the anticline axis and the forelimb. We observe no subsidence in the footwall as well. And so from this signal, we infer that the bedding of the sedimentary, the folding of the sedimentary layer is due to is caused by the fold step over ramp. So it's the fold propagation fold geometry, and constraint on the tip of the fault where there is this maximum of shortening, and the forelimb and the axis of the fold where you have a maximum of vertical. And if you want to go farthest, you could say also that if this long-term surface displacement observed with Sentinel is equal to the long-term deformation of the fold, maybe you could also infer that the gradient, the surface displacement gradient, is equal to, can give you some insight into the geometry of the fault at depth using some kinematic law of fault propagation fault. So to conclude, I think, I hope I give you, I show you here that it's very interesting to perform a time series analysis to study earthquake, because it improves the signal to noise ratio, but also give a lot of insight into the other phase of the seismic cycle that bring other constraints into the fault geometry. Here, more particularly, we have multiple north dipping and south dipping back thrust, and high angle thrust that connect to low angle fault which partition vertically the shortening to produce the short wavelength topography. But we saw as well that the topographic growth is not always coseismic, as the evidence of coseismic slip translated into permanent deformation by coseismic fault buckling, which make me conclude that maybe we should be careful in our interpretation of the complexity of the seismic cycle, because maybe not all the time, this transient deformation are not associated with slip in an elastic medium, but maybe it is also sometimes due to off-fault deformation, which can be anelastic, or due to slip along secondary structures. And as a perspective, we could maybe also investigate the lag between the coseismic forcing and the inelastic response of the crust in order to bring some constraint on the effective viscosity controlling those mechanisms. And that's it for me.
Thank you very much, Simon. So very interesting study, very long time series over different satellite missions. So please type your questions in the Slido interface for Simon. We will take them later. We will move on to the next presentation now, and this is given by Andrew Watson from University of Leeds, and it will be about interseismic strain accumulation on the main recent fault in Iran from Sentinel-1 data. Please go ahead, Andrew.
Great, thank you. That all good?
Perfect.
Great. Yeah, hello everyone. I'm Andrew. I'm a PhD student at Leeds, and I'm a member of COMET, and we're going to be looking at the main recent fault in Iran. So starting off actually with the key points of our study, we've used about 4,500 Sentinel-1 interferograms covering 4 tracks, 2 ascending, 2 descending, and about 5.5 years worth of data. And we've used this to estimate an interseismic slip rate on the main recent fault of about 3 milli below a locking depth of 18 to 30 kilometers. This is the first INSAR interseismic slip rate estimate for the fault. This is also one of the slowest interseismic slip rates that's been measured with INSAR. And this is also the first geodetically derived locking depth estimate for the fault as well. And we've generally found that we are in agreement with previous short-term rates that are primarily from GNSS. So a bit of tectonic background. We're looking in Western Iran, in the Zagros, where about 20-30 mil of convergence between Arabia and Eurasia is driving complex deformation throughout the mountain belt. This can generally be divided into thrust faulting, so range perpendicular motion, and then strike slip faulting, so range parallel. The main recent fault is about an 800 kilometer long strike slip fault. It's right lateral, and it's also relatively seismically active. It's had a magnitude 7 in the early 1900s, and it's had magnitude 6 earthquakes back in 2006. We're going to be looking at sort of this area. These are our INSAR track coverage. So looking at somewhere that are 400 kilometers long, a few hundred kilometers wide. So previous estimates for the interseismic slip rate in the fault come from firstly geological estimates, which generally cover a broader range and tend to be a little bit higher, with the exception of this Alipur 2012 paper, which is quite at the low end of the rates. And then the other group is GNSS studies. This is coming from a relatively sparse GNSS network in this bit of Iran and sort of on the other side into Iraq. And these lean towards the lower end. So yeah, 1 to 5 mil a year is a good band for those. And none of these have estimated a locking depth of the fault for the GNSS, is partially due to the sparsity. So we're interested in, firstly, is the role of the main recent fault in sort of Iranian continental formation. Also then the local seismic hazard. So the locking depth gives you an idea of the earthquake potential, but also is all the slip motion on this one fault plane, or is it distributed? Is the fault creeping at the surface at the rate we can actually observe? And finally, we're using this as a proof of concept for our sort of end project goal of an INSAR-derived velocity field for Iran, and especially the Zagros. So we've been processing interferograms using the LIX automated system, which Tim Wright talked about earlier. I won't go into too much detail on this. There's 2 posters that cover it very heavily, and Tim's talked from before. but we're looking at just this red square here. And so this is producing us interferograms that are paired sort of 3 backward, 3 forward. Once we have our interferograms, we're correcting for atmosphere using GACOS, which can be found at the website link there. And we're also then performing our time series analysis using LixBAS. So this is a open source Python package to do NSBAS time series analysis that was written by Yu Morishita, and strongly recommend people checking out. It's quite a good bit of software. So we're looking at these 5 frames. Lix breaks up its frames into sort of 13 bursts along each of the 3 subswaths. We have 2 ascending tracks, 2 descending tracks to cover the area. For each one, we have about 200 SAR images, and these cover about 5.5 years total, and we make something like 650 to 1,000 interferograms for that. And to give you an idea of our network, this is an example for 006D. Blue connections are interferograms. And then you can also see red ones. This is where LixBAS has done loop closure to check for errors, and these are ones it's automatically removed from the time series. So we have something like this for all 5 frames. So once we got this, we get our line of sight velocity maps. The line of sight arrow is in the bottom left or bottom right corner of each image. And then red is towards the satellite, blue is away from the satellite. And sort of 2 main signals probably jump out straight away. First is this big area. And so this is the 2017 magnitude 7.3 earthquake that sits sort of in the western edge of our study area. It's not on the main recent fault, it's on an adjacent fault. And so that's something we have to deal with. And the other thing that might jump out is these dark blue signals. And these are, if you compare it to optical imagery, they're most likely groundwater subsidence signals related to areas of some agriculture. So we want to deal with both of those before we can have a look at our interseismic rate. So starting with the earthquake, we forward model both the main shock, that's the top reference, and a couple of the aftershocks at the middle reference. And Faye, my colleague, was talking about these earthquakes earlier. We forward model them using sort of a CADA, and then we remove it from the cumulative displacement series that we get out of LixBAS. And so that takes a chunk of that signal, which is up to about 600 mil a year for the step, 600 mil for the step, not a year, and takes it out. The pink squares here are the reference pixels. These are still relative. Once we've done that, what's left is mostly post-seismic. Because our interseismic signal is relatively small, removing that post-seismic accurately enough that we're confident in the velocities we have after is very hard. It's not something we can do right now. And so instead of trying to remove the post-seismic, we just try to estimate the spatial extent of it. We do this very simply by splitting our time series about where the main shock happened, and then just estimating a new average velocity for either side. This increases the error because you have a shorter time period, but it lets us pick out this area here. So this is contoured based on the standard deviation of an unaffected frame, 108D. And in this pink box, that's the location of the main sort of post-seismic signal left over that velocity maps. And so when we come to pick our profiles, which we'll go into a bit more later, than they're shown there, we just avoid the area for now. Something we hope we can improve on in the future, but for now, it's easiest just to not go near it. So next thing we need to do is we need to take our relative measurements, we need to tie them down to something, and we want to decompose them. So we take GNS velocities from Karamitel and create just a smooth north and east velocity field. And we reference our INSAR to that, so in a Eurasia fixed reference frame. And we can then take the north velocities from the GNSS and subtract them from our line of sight. And that means we can then do this decomposition where we can assume there's negligible north-south motion left. And we can then take, for example, our ascending and our descending measurements, the conversion from line of sight to the components, and get out our up and our east velocities. Once we do this, we end up with these two maps. This is the vertical and the west-east motion. So that's positive upwards and positive going to the east. Starting with the vertical, we can see that those dark blue signals are there in the vertical. They're not there in the east-west. So it's coming in that mostly vertical motion. They're probably groundwater subsidence. We also don't see any real change across the fault. So that suggests there's no observable like oblique motion on this fault as well. Then looking over to the east-west, we can see relatively faintly there's sort of more positive colors to the north of the fault, especially if we look in the east side of that area, and slightly more negative to the south side of the fault. We take those east velocities and the north velocities from our GNSS, we can calculate the fault parallel velocity, and that gives us a map like this. So again, red here is essentially motion in a right lateral sense. It's going to the southeast, blue is motion to the northwest. And so we can see a contrast across the fault. We have more positive on the north, negative on the south. So what we want to do is try and model this to get out the interseismic slip rate and the locking depth. So we take 3 profiles. We split these up so we can account for the slight change in the strike as we go around, which goes from something like about 300 to 315. And then we model this just with a simple 1D screw dislocation along the profiles. And we do it in a Bayesian Monte Carlo sense, so we can estimate the posterior distributions. So we'll start with profile A. And just to build this up, we'll start with just the median elevation along our profile. That's the gray polygon. We'll add the fault parallel velocities projected onto each profile. We'll add the mean in a window along it and the uncertainty on that. That's the 1 sigma. And then any GNSS profiles, points in the profile, which there is not many. And then we add our model solutions. So this is a uniformly, randomly selected 1% of model solutions that our MCMC generated. They're ranked from yellow, which is best, to pink, which is worst. So they give you an idea of the fit here, that they are fitting the general trend of sort of more negative fault parallel velocities on the left side in the southwest, more positive on the right. If you look at this in a map view, we can see that the model in the middle does a pretty good job of flattening off those residuals. So there's a lot of noise, a lot of other things going on. And then when we look at this in the posterior distributions, so we have a slip rate of about 2.6 mil a year with pretty good confidence interval. And in the distribution, the slip rate is quite well constrained. It's nicely Gaussian. What we see is the locking depth. While we have a lower bound, the upper bound's relative is unconstrained. It just rolls off. So we see a similar result where we look at profile B. That's this middle one. Again, we have a pretty good fit of the model solutions to the data. The model does a good job of flattening off our residuals. It seems to be a good fit in the map view. And our slip rate, again, good Gaussian posterior, 2.9 mil a year. Nicely in agreement with profile A, but the locking depth is poorly constrained in the upper bound. This one's better. And again, we've got a depth of sort of 18 and 19 kilometers. That upper bound is still relatively constrained. Finally, if we go along to profile C, notice from the dots on this one's noisier. There's quite a bit more stuff going on. The model still does a relatively good job of fitting it, but when we actually look at the posterior and the values we can get out, we see that the locking depth just ran into our upper bound. So that is pretty much unconstrained. The slip rate is still very reasonable at 3.5 mil a year, but it's been dragged to a higher value by that trade-off with the high locking depth. Basically, for this one, there's too much movement in the far field, and there's quite a bit of noise close to the fault in the near field, which makes it quite hard to constrain. So this led on to sort of a final question of, can we improve this modeling and better constrain the locking depth? And so what we try is modeling all 3 profiles at the same time. So we model each profile for an individual interseismic slip rate and an offset. That's just the scale offset up and down. But we make them share a locking depth that we then solve for. And so this gives us some results like this. So our models are still, again, pretty good fit to our profiles. Our slip rates are all very reasonable. We see that CC comes down to a lower value. So 2.6 to 3.1 mil a year. And all the uncertainties on these are 2 sigma are above 0. So we can at least be relatively confident the fault is moving in the right direction. The locking depth we get out, the value is 29 kilometers. It's a bit higher than our previous estimates, which were 18 and 19 kilometers. It's also a little bit higher than what we'd expect from the seismology. So you generally see centroid depths at something like down to 15 to 20 kilometers, sort of maximum depth. So that's more where we would expect. But the uncertainty on this is still overlapping with our 2 previous estimates. If we look at this in the posterior as well, we can see that the locking depth, which I'll draw you to here in the red box, is better constrained than the ones. We have a distinct upper and lower bound, although there is quite a bit of kurtosis on this distribution, so it has quite long tails. So coming to our conclusions, we've estimated a slip rate of about 3 milli. Yeah, this is one of the sort of slowest interseismic slip rates that's been done with INSAR. And we've got an error on it, probably about plus or minus a milli to about 95% confidence. This is in agreement with those previous short-term GNSS rates and that Alipur paper and some of the lower end of the geological. And this would account for something like 15 to 30% of sort of the range parallel convergence across Iran. And finally, we've estimated a locking depth. This is the first one for the fault. It's relatively weakly constrained. So we're saying 18 to 30 kilometers a year. The reality is probably in there. When I highlight the difficulty, even with this much Sentinel-1 data, that when you have a very small tectonic signal and quite a lot of noise, especially close to the fault and in the far field, it is hard to constrain locking depth side of things. But maybe it's something we can improve in future. So thank you very much for listening.
Thank you very much. Very interesting. It's so beautiful to see all these displacement maps. I'm handing over to my co-chair, Paul.
Hi. Yes. So we're moving on to the. Do we have the third speaker? Or he was not. He got dropped off. Yeah. So we're moving on to the fourth talk, which is interseismic strain accumulation and fault creeping behavior detection at shallow crust along big faults over Tibetan Plateau region by parallel processing of Sentinel-1 INSAR time series by Jianbao Sun and Jiangtao Chiu, and the speaker is Jianbao Sun. So go ahead.
Can you see the screen?
Yeah, it looks great.
Okay. Hello, everyone. I will give a quick presentation about the recent work on Tibet region PSC INSAR detection and some recent results. This is my outline. It's basically this is methodology development. The application is still on the way. So I will give some most recent result of the application of the PS method in Tibet. Now we have a lot of Sentinel-1 INSAR data, which is available from the global area. So I'm focused on the East Tibet Plateau region. So INSAR deformation in this large scale for interseismic strains detection is similar to GNSS point measurements. So we can use it for large scale in interseismic deformation detection, because INSAR data is in very high spatial resolution, but it is in 60 or 12 days temporal resolution. So we can use it for the whole Tibet region deformation detection, and also some very large and big faults in these areas. So it is because the current data with very small baselines, both spatial and temporal baseline is very small. So the coherence is very good everywhere, even in the Tibet Plateau region. So we can use it to do the slip rate estimate. But we are also considering use this data for slip rate temporal behaviors of these faults, big faults, or the whole plateau regions. So in this study, we are still on the methodology development. So we will discuss a little about the limitations of the current methods. This is a GPS network derived products we have. My colleagues published last year. So these GPS points accumulated in the last 20 years. So, and the right side is range rate derived only from these GPS points. GPS points, there is already we have thousands of GPS points across the whole mainland of China. But for some area, especially to Plato, we still lack some good coverage of the GPS stations. So maybe using INSA data, we can supplement this shortage. So my colleague uses the GPS network and post-seismic data of the Venture earthquake to infer the 3D deformation of the East Tibet Plateau. So previously we used only SAR data from NVSAT ERS 1.2. This kind of data has very large baselines, and the sampling is not good. So we just use GPS network to do the work, and also some vertical motion detection using continuous GPS stations. You can see very sparse distribution of the GPS points. But this we already have much more GPS stations across the whole region. So this is still under updating. But earthquakes always occurred along very big faults. This is a very large earthquake occurred in the past 20 or 30 years. So you can see the red stars are big earthquakes happened from 1997. So most of the earthquake occurred along very large, very big faults. But we also have some exceptions. The recent one, we call it a Mado earthquake, occurred very close to the Kunlun fault, but it's not on that fault. So it's on the earthquakes occurred to the south of the Kunlun fault. This is the seismic deformation from the INSAR deformation detection of the earthquake deformation. You can see very clear that that's a seismic deformation, but the big fault, the Kunlun fault, is the red line. So it's the earthquake fault is not on the Kunlun fault, but it's very close to it. So for big faults monitoring, we use a GPS network, but it is always very few of GPS points across these kind of faults. You can see that this is East Kunlun fault from west to east. The GPS velocities have some gradient. This displacement gradient is reduced from east to west to east. So the earthquake occurred just between O and P, profile O and P. So you can see across the Kunlun fault there is the gradient, displacement gradient, just a fault parallel. This is a recent result about the GPS calculation of the slip rate across the recent earthquake fault and the Kunlun fault. You can see the displacement occurred just the major occurred on the major earthquake fault, the Kunlun fault. The Mado earthquake fault has almost no gradient could be seen. So this is the real faults in the field. We can see the right side is the inside deformation. You can see almost see nothing across these faults. So we use inside one to detect the who deformation occurred along this big profile from north to south, which covers Haiyan fault, Qianxuhe fault, and the Kunlun fault. The two faults has well-known creeping signals occurred, and the Kunlun fault is a major boundary we have known. And we are focused on this area and use 6 frames inside data. We can make PS point detection and do the further analysis of the deformation. So this is the method we used. It's very much details given here. We can use the Hooper's code steps to do the seismic ground deformation detection. Use 6 frames. This is 1,000 kilometers along track and 250 kilometers across track. So we obtained 41 PS per kilometer squares. So if we reduced it, want to use cost resolution, we can reduce it to this kind of points. So it is possible to do the analysis for very small computers. So in this conventional processing, we do some changes on the steps code. We mainly use Gamma's MCF special Arabic code for this help to reduce Arabic errors. But except this, we also use a new method to do the analysis. We use the use a PS identified use the steps method. But after that, we use a PS method to form the sparse network. So the sparse network use only those PS points to do the interferometry, and we form the interferometry so that we can use phase closure to detect phase Arabic errors. But mostly important is that we can use common synthesis stack, or the method developed by Fiaca's group at UCSD, and which is can be used for estimates APS. Then we use the APS estimate for each acquisition and remote from the PS network. Then do the rest standard PS processing. We can reduce greatly the atmosphere signals. So this is a standard PS processing we used. You can see there is in this track there is a big size, big SAR data gap. There is no data we can use to connect from north to south. This is a standard processing results using steps. You can see very clear from the north is a creeping signal here, and there is a small fixed subsidence. And also here, this is Qianxuhe fault, which is slipping very fast, mainly from the surface scraping. And there is a very hairy phase jumps here. So this is a standard PS processing, but we updated to use the new wrapping strategy, and we do the seismic, we do the deformation detection. So user refinement, we can see that most of the errors around here, which was effectively remote. If we select the 2 points to see the time series, this is a point here. You can see there is a linear feature here, and there is south of the Qianxuhe fault also some kind of left lateral motion. In this processing, we remove phase wrap, use only this direction, along track direction wraps, so that we do not remove real signals. So this is our refined wrapping method in steps for this processing, but we use a new method is like this. If we form use identified PS points, construct this kind of sparse network, we can get this. And we use common synthesis stacking technique to do the APS estimate. There is some data you cannot do estimate of APS using method, so remove some data. You can see this is the result we obtained. The left side is from common synthesis stack estimate of the reference image APS. The right side is APS estimate from steps processing. You can see very similar between these two images. So we further to compare the time series of the selected points, we can see that the displacement here, you can see very the scattering of the points becomes very stable. Even it's not very linear, and it's variable with time. But you can see that the uncertainty is greatly reduced, and we also see that these 2 points across the Xianqu fault. We select 2 points, one across the fault. So you can see that these points have some very strong temporal variation. Currently, we do not know what kind of signals it is, but the sleep rate, the average velocity is very clear. We want to confirm that the temporal variation is not just pure nonsense. We estimate the difference between the left side and right side across the Xianqu fault. You can see there is very linear or with some nonlinear features across the fault displacement. So we think the method greatly reduces the uncertainty of the time series deformation detection. So the last thing we want to do is to do the correction with continuous GPS stations to do the analysis. So this is a case we used. You can see there is sorry.
The time is almost up. Yeah.
Okay, I'm broken. My network broken. Sorry, can you see that?
You're back. Yeah, we see it. If you could wrap up pretty soon, though.
Okay. Sorry. This is the conclusion. I summarized. It is possible to do the PS detection and the deformation extraction use PS method in Tibet Plateau regions. A time series with multiple frames of Sentinel-1 data in full resolution need some parallel processing. So this is what we've done. You ought to estimate phase closure of PS points, also do the APS estimate using common synthesis techniques. We formed a sparse network using the identified PS points. And finally, temporal variation of PS displacement maybe can be refined using the continuous CPS stations in the future. Okay, this is my short presentation. Thank you.
Okay, thank you. All right, we need to move on now. We're moving on to the last talk in the on the as schedule, and that will be the title is Seasonal Deformation in South Iceland from INSAR, Influence on Earthquake Activity, and that's by Sigurjón Jónsson and Yunmeng Cao. And the talk will be given by Sigrun Jonsson.
Yes, do I need to switch displays?
It looks perfect right now.
Looks perfect. Okay. So good afternoon, everybody. Great to see you at FRINGE. The topic that I'm going to present today initially had actually nothing to do with INSA. And it's something I was working on a couple of years ago, but then put on the shelf. But seeing FRINGE coming, I would say, well, maybe we can do something for this project with INSA. Did it work? Well, maybe a little bit. Let's move into this. What's the motivation here? Now, there's astonishing, if you look at historical earthquakes in South Iceland, that they seem all to occur in early summer. So if you look at the last 100 years, kind of noteworthy earthquakes, they are in May, they're in July, June, May, and May again. So is this really a coincidence? Well, it doesn't look like it. But let's look at the tectonics a little bit. So this is map of Iceland. It's on the mid-Atlantic plate boundary. We have a divergence about 2 centimeters per year across these plates ridge segments, and then they're connected with these 100-kilometer long transform zones. In the south, it's the South Iceland transform zone, a left lateral transform. And if you zoom into that, this is approximately the location of the large earthquakes in the past 300 years. And they delineate very nicely this east-west trending zone where you have this left lateral transform motion. However, there's not a big left lateral transform fault. The earthquakes are taken up on these short vertical north-south right lateral slag slip faults, a case that we often refer to as standard bookshelf tectonics. So this is where we are looking at these earthquakes, and this is one of the two areas in Iceland where the large earthquakes take place. So what do we know about these large earthquakes? Well, going back in the history, there's something like 34 earthquakes in the last 800 years that have been classified as damaging earthquakes. And when you're testing seasonal occurrence, you have to avoid having dependent events. So dependent events, sometimes these events occur in pairs or the sequences of them. So after looking into this, we can say that the timing of at least 24 of these earthquake and earthquake sequences is independent. And if you look at a histogram, just with the months on the x-axis, you can see they seem to peak in the summer. But is this significant? Well, let's look at a way to test this. You can look at a phase diagram random walk test, which is called a Schuster's test, where you basically, for each earthquake, you step in the direction of the season it occurs, and then you look at the significance level. So by doing that for these 24 independent earthquakes, we see that, in fact, there is only less than 0.5% probability that an occurrence pattern that we see in South Iceland is purely due to chance. In other words, there appears to be some seasonal process that is affecting the timing of earthquakes, making them to occur more in May and June than the other parts of the year. So what could it be? What is influencing the seasons? Well, obvious thing is to look into the weather. Looking into the weather, Iceland is a temperate climate in the middle of the Atlantic, so you only have a 10-degree difference between summers and winters. The winters are cold and the summers are also cold, so it doesn't really change very much. If you look at the rain, precipitation is actually at minimum in the summer. That would tend to reduce pore pressure, would tend to move things away from failure. But the difference is actually very small. It's rainy in the winter, it's also rainy in the summer. So it's raining all the time and it's cold all the time. And what about atmospheric pressure? It peaks in the summertime, and that would also tend to move things away from failure. You just press on top of everything and you clamp these faults. And so it seems to be an anti-correlation to the timing of the earthquakes. But it's also not a very big change. It's a small change. It's always windy. So in summary, it's cold, wet, and wetty all the time. So not so much difference between seasons. And what do we see then? Well, we can see clear annual variations in vertical GPS time series. So this is a map of South Iceland again, as just an example, continuous GPS stations where you see these seasonality signals. Another thing that is quite striking is that stations in the eastern part of the zone seem to be uplifting fairly fast, while in the west, they are uplifting less. So you have this differential motion. And the reason for this is glacial isostatic adjustment. Center part of Iceland is moving up very fast due to ongoing mass loss of the ice caps, as well as recent ice loss in the past decades. But if you model this temporal change, so the model the earthquakes and you model out the transients, you end up with the seasonal signals only. And you can see they're similar. This is taking into account annual and biannual signals, mostly annual. You see that in the western part of the zone, it's maybe 5-6 millimeter, the amplitude of these variations, but in the east is slightly bigger. It's approaching 10 millimeters. So what is causing these seasonal variations? Well, it's been shown already that it's mostly due to snow load. Here's a map of Iceland showing, basically the circles are showing how much snow there is. It's mostly in the central part of Iceland, and the color tells you something about timing. What is maybe noteworthy is that there's a very little snow load directly in this area of South Iceland. So most of the seasonal displacements are actually due to load changes, these are to the east and to the north. And therefore, we have bigger seasonal displacement in the eastern part of South Iceland seismic zone. So this is what we have been looking at. And then I just started to think, okay, can we do something with INSAR here on this problem? So Yuman Kao has been working with me, and he just said, okay, yeah, let's look at this. And he started processing data. Instead of focusing on South Iceland, he just decided to process all of Iceland. You can do that in 3 parallel tracks and 3 descending and 3 ascending tracks, and something like 1,800 images and data from 2015 to 2020. Now, one problem with processing Iceland as a whole is that because of the snow cover in the middle part of Iceland, you cannot really use scenes from October to May or to April. So it's only about a third of the year that you can have a reliable scene. So this, of course, obviously starts to limit our possibility to resolve seasonal displacements. But let's see what comes out. Well, for that, for the strategy was fairly typical. Lots of interferograms, obviously, corrected with this new atmospheric correction method based on global atmospheric models called ICAMS. It's recently published. You can try it out. It's supposed to do better than some of the other GAM corrections because it uses smarter interpolations. Then with some proper weighting, produce time series results, look at the velocities and potential transients, and then stitch this together and look into near vertical and near east. So pretty standard here. But let's look at some results. So here for the descending passes, for example, here you can see the rate map. And if we put these things together, you see a beautiful map of Iceland. The red colors are up towards to the east and to the up towards the satellite, while blue is down and away. You see it's approximately plus minus 2 centimeters per year here in this rate map. Now you can also look at the ascending. Again, here 3 parallel tracks pumped together. Red is up and towards the west, while blue is down and away. Now you can then take these velocity maps and play around with, for example, east-west velocities, which are quite nice for East Iceland because the plate motion is mostly east-west. This is more or less in a North American reference frame. So you see the eastern part of the country moving away about 20 millimeters or 2 centimeters per year, which is expected. The arrow there shows the direction of relative plate motion relative to North America. And what you can also see here is that the sharpness of each, we see the boundary popping up. So the transition is different in different places. So in the north, for example, you more or less have a transition in 30-40 kilometers. In the middle, it's very, very diffuse. And in the south, it's very, very sharp. So you can, of course, play with modeling this by looking at locking depth. We can't do that often with faults, but when you're looking at extensional areas, the physical quantity that you get out, the locking depth, doesn't really have any relation to reality. It's more just a reflection of how diffuse the deformation is across multiple segments of that extensional boundaries. Now, that's not the topic here. I want to look into the near vertical. Now, this is ignoring north. And what you see here is strong movement up towards the sky. Iceland is popping up like a cork in response to reduction of ice mass. So it's mostly GIA, or glacial isostatic adjustment. This is both currently occurring ice loss due to global warming, but also in the recent decade since the last glacial maximum in 1880. So this is about 3 centimeters or exceeds 3 centimeters per year. So it's quite a strong signal. What you see, but this has also been already been looked at by, for example, Duran and Sigmundsson a couple of years ago. Our rate map is improved in the sense that it has 2 more years of data. It's full time series analysis results instead of interferogram stacking, and also has atmospheric corrections and some other things to it. So we believe it's a little bit improved results from previous studies. Now, what you can do with this also is it's a little risky, but it can be fun to look at some other things than just velocity. So you can actually look at, for example, increase in uplift rate. Now, this is a pretty noisy plot, but what you start to see is some discontinuities between tracks. But what you more or less see is like a little bit more red than at least the light blue is. And this could be an indication of an acceleration in uplift rate. And this has been reported in GPS already, but I'm not so confident with it here. What I am more confident is that these volcanic centers are showing up. So Krapla, for example, it just recently changed from slight subsidence to slight uplift, Torvjökull as well. And then Reykjanes has been in the news a lot because this red blob there is due to renewed uplift in Reykjanes that started early last year. So a rapid change to uplift. That eventually led to a dike intrusion, which is here in Reykjanes, very close to the city of Reykjavik, only about 25 kilometers from the city of Reykjavik. Just here's a snapshot of the deformation in February and March. And then on the 19th of March, it made it to the surface. It was a clear dike intrusion. It is a near vertical displacement with nice uplifting flanks and subsiding middle. And it made it to the surface on the 19th of March and it's still ongoing. This is just a drone shot I shot last week when I went to visit the site. It's absolutely a spectacular site. The crater there is about 100 meters high, and it's bursting out every few minutes. And I have to say, I mean, for the first time in 800 years, the skyline of Reykjavik is looking pretty dramatic with a backdrop, and you have the lava fountaining in the back. It's not always nice like this, but it's been quite an experience for people living there. Now, back to the uplift. This is the same map as before. Now I'm just looking at some GPS sites, so continuous GPS sites here. And if I look at the uplift just along this profile, there is a nice correspondence between the uplift SIN in GPS and INSAR. Very little in the western part of the zone, very strong, about over centimeter per year in the eastern part of the zone. So here the difference is very, very small. But we are actually more interested in the seasonality, so not really the uplift, so seasonality. So let's go back to this slide and let's look at how the seasonal signals compare to the seasonal signals in GPS. So now I look at these 2 sites in a little bit more detail, and you see the seasonal signal, the vertical rate. And if you look at the time series results, it's actually we recovered the rate, but the seasonal signals don't look right. They're very noisy. And why is that? Well, there is a couple of things here. The reference point is 200-300 kilometers away. We need to have it very far away because the whole country is going up and down. We cannot really pick a reference point very close by. We go across some track boundaries. And this is actually not a line of sight uplift time series. It's a vertical time series built out of multiple line of sight observations. But we can try to improve this just to do a little bit of atmospheric phase screen, you can call it, or space-time filtering, and then you start to approach something that is at the similar noise level. Of course, this you can tweak even further if you like, and just do like some subsidence people, and then you start to get these piecewise continuous curve that appears to indicate that there is a clear seasonal signal here that we can also recover. But we basically are missing quite a few dates in between due to the snow cover, although we could do, I think, a little bit better by looking at the scenes in between here because of the relative lack of snow cover. Now, if you look at the differences between across the zone, you get a large velocity difference. This is just the difference between the 2 GPS stations, but then the seasonality disappears. So that's because the amplitude of the seasonal signal between these 2 sites is not so large. So the whole area is kind of breathing up and down in response to snow cover, which is actually pretty far away. So you can do the same kind of things. You more or less recover the rate, don't see much seasonal signals. So what are we doing with this? Well, we are looking at the loading, snow loading. So we look at this area and we can see it's mostly relatively lack of direct snow loading, but we can model the displacements. We can model the displacements expected from atmospheric, ocean, snow, and glacier loading. So here you see one seasonal cycle of predicted displacement in the center part of the zone after adjusting the amplitude. You do that by changing the stiffness of the crustal and subcrustal material, and then you can compare it to the average CPS displacement. You can adjust this, and it turns out the phase matches very well. The amplitude, as like I said, you can optimize on the amplitude with the stiffness, and from that you can then look into stress changes, and that's what we are really after. We basically want to cut the South Iceland here in half. Let's look down into the Earth. The faults are vertical, north-south faults. And we are interested in the loading stresses, to the east-west loading stresses and the shear stresses acting on this fault. Are they significant to possibly promote or demote earthquakes? Now,
say, Shani, it's up. You're pretty much at time, so if you could.
Yes. Okay. I will say this. So basically, what we see is that loading is compressional. It causes negative stresses. But we see the maximum earthquake rate where we start to have unloading rate. Unloading rate is peaking. However, it's a very small rate, and we think all the processes like pore pressure changes are probably more at play here due to spring snow melting. And that jumps to the conclusions. Many large earthquakes in South Iceland in May and June. Seasonal snow and glacier loading cause clear vertical displacements. INSAR rate agree, but we don't really yet have added information from INSAR here for this particular project, although we have a lot of other interesting information from it. Seismicity rate correlates with unloading stressing rate, not total unloading stress, but the stresses are small, and therefore we think pore pressure changes due to spring snow melting could easily cause 10 times larger stress changes, and therefore would probably be more at play in promoting earthquakes in spring and summer. And with that, I stop.
Great. Okay. Thanks. Great talk, and nice video as well. So we had to skip our third talk due to technical issues on for the speaker. So we're now going to try and go back to that. Do we have Sami? I don't see.
Yes, I'm here. If you hear me.
Oh, okay. Great. Yes. So. The final talk that's going to be presented, which was the third one on the schedule, is the title is INSAR-based earthquake slip inversion facilitated by statistical hypothesis testing, and the authors are Shima Nazarizadeh Mahani, Sami Sameh Esfahani, and Abdulreza Safari, and the talk will be given by Sami Sameh Esfahani. Sorry if I mangled your names.
Yes, great. Thank you, Bob. Good afternoon, everyone. I hope you hear me well. This work, as Paul read the title, is about some application of a statistical hypothesis testing in slip inversion that we did here in University of Tehran. You can go to next slide.
Who's controlling the slides? Ryan, can you go to the next slide? You seem to have lost.
Okay, thanks. So this is the importance of slip distribution and slip inversion. I'm not explaining that much here because this is so here we see the mathematical model that usually common methodology in the slip inversion. We have vector of y, displacement observations from geodetic data or INSAR. We have S, vector S, that is a slip of the patches on the discretized patch. We have observational errors, and we have design matrix that it's usually using from Okada dislocation model or some other models. The main point here, this as you know, this mathematical model is usually ill-conditioned system, and it needs regularization, some sort of a smoothing. If we go to next slide, So the most common method for this regularization is the second-order derivative of Laplacian regularization, or second-order Tikhonov regularization that puts some smoothness as this kernel L on the slips, and alpha is a regularization or a smoothing parameter. So there are plenty of different methods to choose alpha. Or recently, in the next slide, we see that there are other methods. If you go to next slide, that use, instead of Laplacian, they use some sort of statistical property of the sleep behavior. We assume the sleep is a random function on the fault, and we assume some stochastic properties of that. For example, self-similarity behavior, Wong-Karman covariance or autocorrelation function, Gaussian, exponential, different kind of statistical constraint we can put there to constrain the sleep and solve the ill-conditioned problem. In the next slide, we see the motivation of this study. That usually, often, different regularization methods provide comparable misfit to the data. It is difficult to decide which one is better. This is just one very simple example on Chile earthquake that you see the wrapped and unwrapped interferogram. In the next slide, we see the estimated ST from two different methods. You go to next slide. Yeah, the one on the left is self-similarity regularization, and the right is Laplacian regularization. You see quite totally different sleep behavior between these two methods. But if we look at the misfit in the next slide, you see that the misfit data is very similar between these two. So on the left, we have data. On the right, we have a model from two different regularization. And on the right part, we have a misfit, very similar misfit. So if we just look at the data, we should say both sleep behavior makes sense here. But which one really is, can we statistically determine which one is better? Does it make sense to do that? Or can we leave it here and say, okay, that's what we should do, that we can do, and then we should geophysically interpret it? Or we can statistically say which one is better. That's first motivation of this study. Next slide is the second motivation. That we have this leakage problem. That a lot of, when we do this smoothing via one of these methods, a lot of sleep from its leak to non-sleep patches. In this figure, we have results of one simulation. The blue area, it shows the rupture area that we assume a sleep there. So everywhere outside the blue area, we assume no sleep. However, when we do regularization and when we find a problem, we see all these yellow areas around the rupture area. That this is the leakage of the main signal to the surrounding area of the rupture. So the second motivation is how can we use the statistical testing to identify slipping patches. So identify the rupture area and constrain the sleep behavior better. If we go next slide. So let's look at the first problem. If we assume our observation is normally distributed with the expectation as a mathematical model Okada AS and the QY as the variance covariance matrix of the observation error, and we assume S sleep has a normally distributed zero mean and our regularization or variance covariance that you put as a constraint. In case of Laplacian, we also can formulate it as the variance covariance with the equations that we have. So then we can have a regularization, but regularization here, then it's equivalent to maximum a priori estimator that we have. So it is a statistical, actually, interpretation of regularization. So this objective function that we want to minimize here, the red box, it can be proved that has a square distribution with the degree of freedom equal to m minus tau. M is the number of observations, number of insert data or reduced insert data that we have. But tau is important. There is an effective number of unknown parameters. It's not equal to the number of patches. if we don't do regularization, this is the number of patches or number of slips that we make. However, because of regularization, we actually put some constraint on it, and this effective number of unknown patches, then we can compute it. We have an equation of that on the right. I don't want to explain that much the theoretical aspects of that, but the tau means how many unknowns effectively we should estimate. It's much less than the real number of slips that we want to estimate. If we go to the next slide now, so we have the distribution, chi-square distribution with degree of freedom. The expectation of that is m minus tau, or we can call it degree of freedom. And then we have a regularized slip, or we call it here x hat or s hat in our previous slides. This objective function that we get from our estimated from our estimation. So this red line and black line in between, when they are closer to each other, it means the posterior probability of the solution is higher. So actually, if we have different regularized solution, the one with the minimum A minus degree of freedom, the box in the below of the slide, in the lower part of the slide, our argument here, the one with that minimize this is we can say statistically the pattern that you find from a slip, it's better match the assumption or constraint that we put if we have different kind of constraint or regularization. Let's look at the next slide, some experimental results from it. So we have 4 different regularization here on the Chile earthquake. From von Karman, exponential covariance function, Gaussian covariance function, and Laplacian routine or standard way that we do. And if you go to the next slide, we already see that the misfit of all of them are very similar. But if you look at the last column here in these slides, we see that the von Karman regularization perform much, much better based on the objective function that I show you here. So we argue that then in this case, it showed that the von Karman regularization has a better posteriori probability. And of course, all of them have a more or less same misfit, but this one is the better choice. Here, one important thing is the first column, is this effective degree of freedom. If we look at the first column, we see all of them more or less are in the same order. It means the level of constraint that we put in the model between these 4 are more or less the same. If they are not the same, then I was doubting about this method because the method that put more constraint on the data maybe get a higher posteriori probability. So then it's not a fair comparison that says this is better. However, here we show that the level of constraint in these 4 regularization are the same. The amount of constraint that actually we impose on the model. However, the probability is much, much higher for von Karman. So then between different regularization methods, we can choose which one is better. If we go to the next slide, is the second problem, the leakage problem. Next one, slide 17. I already introduced the problem. We go next slide. Okay, when we estimate the sleep for each patch, we estimate the sleep and its variance. So this equation for a sleep is the first equation. Second equation is the variance covariance matrix of the, it explains the stochasticity or precision of the estimated sleep. So the diagonal elements of this variance covariance matrix actually is the precision or accuracy of the estimated sleep. In the next slide, we formulate the hypothesis testing to discriminate between the sleep patches and non-sleep patches. Null hypothesis is that the estimated patches, the expectation of that is 0. It means that this patch is non-sleep patch. Alternative hypothesis is that we have a significant amount of sleep, so the patch I is a sleep patch. So this is the alternative hypothesis. Here, under null hypothesis, the test statistic will be the amount of sleep that we estimated divided by its standard deviation, that this should follow the standard normal distribution. Here I made a mistake. I put the normal distribution with the variance, but the variance here is 1 because we already divided the test by a standard deviation. So then for non-sleeping patches, the absolute value of this test statistic should be smaller than the normally distributed data on alpha, half of alpha. That's a significance left. So based on this simple test, we can decide which patch is slipping and which one is not. Then next slide. So after identifying the rupture area, it means which patch is asleep and which not, then we should iterate. So then we do regularization again, but this time the non-slipping patches we exclude from the inversion, and we iterate till converge. This is one simple simulation. This is a slipping area based on the von Karman. This is very simple, so very fast transition from a slipping area to non-slipping area. But if we go next slide, and based on this sleep, we simulate data, we add the noise, we make the interferogram, then we do regularization. Let's go to the next slide and let's see the results, because simulation, I think, is easy here. Everyone know how we simulate
Sami, to still have time for questions, right? We need to wrap up.
Yes, so it is, I need 30 seconds.
Problems.
And here, then we see, then with decreasing the level of significance, more patches are removed, and we see that when we have a leakage problem, the sleep was underestimated a lot. So this hypothesis testing works very well here to identify exactly when where the rupture area is and estimate the sleep better. Next slide, this is just how we choose this significance level of the test. It is a little bit subjective by simulation. We do simulation a lot of times and see where with which level the results for us. And here in this case is 35%. It is, I wrote there, it's subjective a little bit. That's it. Next slide is just summarizing what I said. Thank you very much.
Yeah, thank you very much, Sami, for your presentation. And with persistence, we overcame technical and maybe political borders. So thank you, everyone, for the presentations, and also for the audience for the patience with these technical problems. We now have time for questions, and we received some questions from the chat. I will just start maybe with the first two ones for Andrew. So Andrew, so there's a comment that this was a very interesting talk. And the question is, what are the main contributions in the residuals, remaining atmospheric components or some local deformation signals?
And cheers. So my guess for the noise would be firstly leftover atmospheric. The gauge loss correction isn't as good on anything that's sort of turbulent noise less than 75 kilometer wavelength, remembering from the paper. So there's probably a bit of leftover atmosphere. There might be some of the short baseline bias. The area is generally relatively arid, but when there's agriculture in the valleys and things like that, those valleys might be more biased than sort of the hilltops next to them. And then close to the fault, there are some cases of things like pull-apart basins, and also because the fault is partially inherited the trace of the main Zagros fault, you quite often have hill next to valley with the fault in the middle, and so you can end up with quite contrasting noise levels right next to the fault. You can have a basin where you've lost a lot of your coherence and it's right on your fault trace. So that's my guess of the combination of what the leftover noise is.
Okay, very good. There's another question, and then we maybe go to someone else first. In your inversions, Andrew, from the velocity profiles, do you mask pixels that probably register non-tectonic signals, or use some measure of noise as weight? And would that make any difference?
Yes, this is something I forgot to mention. So firstly, we mask the line of sight velocities using a bunch of parameters LXBAS makes, like the average coherence, the number of images, the number of loop errors. So that takes up some of the bad pixels. We then weight the data in the profiles using a spatial covariance function, which we calculate from the east velocities after we've masked any large places where there's large vertical signals, removed any tectonic signal from the fault by just modeling it at like 3 mil, and deramping the entire thing as well. So We haven't specifically outside of that tracked down pixels that we think like this is specifically an error, but it is spatially weighted with both variance and covariance.
Okay, great. Shawnee, there's a question for you. How did you overcome the winter gaps in the INSAR time series data using 1-year interferograms? This one is from Sabrina Metzger.
Yes. So we did that, just like she suggested, with 1-year interferograms.
Okay, and then a question.
Yes.
Yes, very good. And are there any direct measurements of pore pressure changes in wells or something like this? Tim
Yes. Also, yes. Slightly more complicated answer. I did not have time to talk about the pore pressure side of the story. It's quite a few other slides, but yes, there are plenty of borehole measurements. They are a little bit problematic because many are so sensitive to surface water, so rain, and so very quick. And that's quick responders to rain, and then you don't want to take those as proxy to what the pressure or the head might be at a kilometer or two or more in the earth. Another thing is that some are in production, and this is another challenge when you're looking at wells. But what I can say is for those that have looked more promising, we can easily, well, from season to season it varies, but you can easily see multiple, well, 1 meter to 5 meter seasonal changes in many, not many, in several wells. And if you would play with diffusion models, this could easily translate to 1 or 2 meter head changes at 5 kilometers depth. If you then it's just a question about timing, how fast it goes down. So that would be easily 10 times larger stress changes and stress rate changes than we see due to the loading.
So maybe we need to, another question was for Jian Bao. And the question was, why is there a gap in data from 2017 to 18? Was it a problem from the processor? And how do you validate the quality of your very large scale product? So.
The data problem, there is a gap in 2017. This is because we use 6 frames concatenated together to do the processing. So there is some data in the south and some data to the south, but there is some data lost between. So we went to do the processing all the 6 frames together. So we just select those data. Therefore, for the variation of the large scale deformation, we just rely on the GPS data. But currently, we only have average velocity. We are waiting for the GPS time series. Uses this GPS time series could be used for refine the INSAR measurements and do the validation with GPS.
Yeah. Thank you. There's another question for Andrew, and it said, so when a fault is at the last stage of the long seismic cycle, its slip rate may be smaller than the long-term average. That's the question. That's how they pose the question. Rate. So it's maybe smaller than the long-term average rate given by geological investigation. So does it mean that the MRF is near rupture as the current slip rate is lower than the geological rates?
Yeah, so 2 quick bits on that. Let's see, we've got 1 minute left. Some of the range in those geological average estimates are to do with when they think the main recent fault started moving, and that ranges from something like 5 million years ago to like 20+ million years ago. And so the range of offsets they calculate is generally a much narrower band, but depending when you start it, that partially gives you that sort of like, it could be 3 mil, it could be 15. And the GNSS would maybe suggest it's the shorter one of those. Otherwise, the fault did have this magnitude 7 in the early 1900s, which ruptured relatively big portion of the fault. But we did also look at if we assumed our 3 millimeter year rate, sort of on with its error, so 2 to 4, and a locking depth of like 20 kilometers, that would give a repeat time for a magnitude 7.3 fault, something like 300 to 600 years. So if that were added up, it would be a while until we'd expect another magnitude 7 on that fault if that behaved.
Okay, very good. So Henriette, do you want to, I guess we're at time, right?
Well, if we allow for some overtime, I would have a question myself for Simon from the very beginning of the session, because Simon, you raised the point that we have a lot of inelastic deformation. So we're talking a lot about modeling, and we're using mostly elastic models. I guess you have a thought about this. What would we do? I mean, when do we stop like using elastic models and need to take care about these unelastic problems? Have you an idea or?
You're muted, Simon.
Yeah, thank you. The first step, I guess, is to identify them by either with in time, because the evolution in time should be different from what expected from after sleep, for example, or from the spatial pattern. And then to model them, I think it's a question that is discussed in the community at the moment, and there's some tools that are developed, but probably not inversion, yes, more direct modeling.
Okay, thanks. We just take in another question for Johnny before we wrap up the session, if anyone is free to leave, right? Johnny, degassing in groundwater related to earthquake occurrence has been reported for North Iceland. That makes me think if there could be some deep fluid reservoir that could react to seasonal loading effects. Are there any indication of it in SIS?
Good question. This is also something that we looked into as a potential mechanism and has been suggested, in fact, as a triggering for all large earthquakes in South Iceland by some people. So we tried, it's a little bit difficult to test this, but one thing that we looked into was to look at seasonality of small earthquakes. And there is some seasonality in small earthquakes. And what is interesting is that the seasonality seems to be stronger among shallower events than deeper events. This made me think is that it's likely a process from above, like increasing groundwater pressure, than from below. So that's at least the argument, the working hypothesis now. But it's an interesting thing, and it has been proposed as a triggering mechanism for South Iceland as well.
Okay, thank you. So before I give two last words from Paul, maybe from my side, thank you very much, all the presenters. Thank you also for the questions. And I would like particularly to thank here the moderators in the background, because we had quite some technical issues. And if this looked smooth from the front, this is due to their hard work. So thanks a lot. And yeah, see you back in the poster session and in the also in the next Tectonic session, which is tomorrow morning. Paul, would you like to add something?
No, yeah, thanks. It was a pleasure. And as you can see, my kitchen is lighter and the sun is coming up in Los Angeles. So time to start the day. So have a good afternoon or evening in Europe or wherever. All right. Bye, everyone.
Thank you very much to all the speakers and the chairs. And I will save the question for you so you can have a look and you can maybe take some recommendation from the question for the Friday session, as I did for the previous session, Henriette and Paul. That will be sent to you directly.
Thank you.
Okay.
Bye-bye.
Cheers, both. Cheers, Ryan.
Thank you.
Bye.